So thank you very much for your really kind introduction. So I'm working on microbubbles. So today I'd like to talk about the microfluidic control and the microbubble generation using this photothermal conversion. So I want to, huh? Yes. So today I'm going to talk about the photothermal heating for the bubble and flow generation. And after some introduction, I'd like to show you what is the vapor-rich bubble. Now I'm mainly working on this vapor-rich bubble. So I'd like to show you what kind of bubble, the water vapor. What is water vapor rich bubble? Maybe I'm a bit sleepy now. Sorry. And then I'll show you how to control the flow around these vapor rich bubbles. And then after that, I'd like to show you how to understand the flow and wall effect using the Stokes thread. So sorry. As I said, my main research interest is bubbles, that is made of gas and they're in liquids. And as you may know, bubbles attracted attention from the beginning of microfluidics as an actuator. So the microfluidics deal with the small amount of the fluid, and the bubbles gives you the method to drive them. And for example, rapid volume change with the phase transition was applied to the inkjet printing. And this is very famous, successful example. And then also the Marangoni effect, that is surface tension differential. And this effect was tried to utilize control the micro machine or other kind of micro robot. So because this Marangoni effect is the force acting on surface or line, so it can be dominant over the body force at micrometer scale. So now important thing is both of these effects can be effectively controlled by heat. So now we can use photothermal heating to control those effects in a very good manner. Within these 10 years, many interesting phenomena or fundamental research of bubbles were done by using this photothermal heating, and there are so many examples. These are some of those, and I can't introduce all of them, but bubble nucleation temperature was examined by Bafo Sensei's group, and also oscillate boiling phenomena was investigated by all Sensei's group, and giant explosive plasmonic bubbles were investigated by Rose Sensei's group, and nano bubble modulation from Carl Sensei's group, and also ballistic motion of nanoparticle and bubble from Tenfei Sensei's group, and so on. So many interesting investigation studies are being reported using photothermal heating. And now we also working on this kind of bubble and flow generation using photothermal heating. Basically, we have photothermal conversion film here and irradiate CW laser on this film and generate heat. Then we can use this heat to generate bubble or to give some temperature gradient on this bubble and generate some flow. So here is the movie of this bubble and flow. So this is the bubble created on the photothermal thin film. And now you are looking at the surface of the photothermal thin film, and these small black dots are the polystyrene spheres just added to visualize the flow. You can see this type of very interesting and rapid flow around the bubble. So this is a so-called Marangoni flow. surface tension weakens at high temperature. So the shear force from hot area to cold area is produced around this bubble. Sorry. And this type of rotational flow can be like applied to salt particle by their sizes. And this such a Malangoni flow is sensitive to temperature gradients so on the bubble surface. So the flow pattern can be controlled by modulating, such as laser power or laser spot position and so on. And also by using alcohol water mixtures, you can tune the flow direction like this movie. So here we utilize surface tension difference between water and alcohol. Due to the thermally induced concentration gradient on this bubble, you can generate rapid flow from now cold to hot side. It's opposite. But this is still Malangoni effect, so-called solutal Malangoni effect. And also, one of the other factors that can significantly change the flow around the bubble is the dissolved gases in water or in liquid. In these movies, now we are looking at the bubble from almost parallel to the substrate surface. So now these small black dots are the polystyrene spheres, just added to visualize the flow. And if you heat up the ordinary non-degassed water, then we obtain a bubble mainly made up with the air. And you can see a Malangoni flow around it. But if you degas the water, and then you can create a water vapor rich bubble here, like with a diameter of around 10 micrometers. And in addition, this bubble induces really strong flow around it. So such strong flow is expected to be useful for microfluidic pumping, mixing, and so on. So now my work, I'm mostly focusing on this phenomenon. So today I'd like to talk about this vapor-rich bubble and flow around it. But then how you then you may want to know how you can recognize the water vapor-rich bubble. So whether the bubble is vapor-rich or air-rich depends on roughly on the amount of air in liquid. So here the bubbles generated in water with various concentration of nitrogen and oxygen, as shown here. So laser was turned on for 5 seconds and then turned off. If the liquid contained a lot of air, then larger bubble will grow. And how much air was contained in the bubble can be determined from the change in size the bubble after the laser is turned off. So here is the time variation of the bubble diameter, like the bubble at this timing, I turned off the laser. So you can see this rapid shrinkage, and then after that, the bubble gradually shrink. So, so this can be understood by the vapor condense instantly, but the non-condensable gases dissolve back into the water relatively slowly. So by looking at this D2, then you can guess how much air is contained in this bubble. So now, so when the water is degassed and oxygen concentration is about like 1 milligram per liter or less, then the bubble will disappear within like 1 millisecond. So after the laser is turned off, then in that case, the percentage of air contained in this bubble is less than 1%. So here let me call the bubbles contain more less than 10% of air. Let me call that such bubble as vapor-rich bubbles. Then let's take a closer look at the moment of the bubble formation in the well-degassed water. So in this case, more than like 99% of the bubble interior is the vapor. So the bubbles to nucleate, the water must be locally superheated above 100 degrees C. So, so initially generated bubble receive energy from the superheated water to glow explosively, and then quickly cool and disappear. Then after that, the relatively small bubble remain for a while. So if the heat generation density from the photothermal conversion is relatively low, then this small bubble disappear, and after a while, the bubble nucleation occurred again. However, above 0.8 milliwatt per square micrometers, once the small bubble forms, then it remains there as long as the laser continues to irradiate. And now I'm working on this small bubble. If you look at this bubble closer, then you can see this is blurred. So this is because this small bubble self-oscillates with a period shorter than the camera's exposure time. This oscillation can be detected by using photo multiplier. Here is the detection result of the bubble oscillation. So the horizontal axis is time and the vertical axis is intensity of detected light. And this light is scattered light from the bubble. So the time variation of the scattered light, the time variation of the intensity of the light scattered by the bubble was measured by using the photo multiplier tube. Then, as you can see, the bubble oscillates with the period of several microseconds. So, and also using some stroboscopic photography, then there is, now you can see there is a moment during one oscillation cycle when the bubble almost disappears. So it is noteworthy that such large bubble oscillation occur under CW laser irradiation. And but why this bubble oscillates so progressively? So the mechanism of the bubble oscillation is currently considered to be as shown here. So first, when the bubble is small, intense evaporation occurs above the local heating point, and the bubble glows. But however, glowing bubbles soon cover the heating point and insulates the heat. So the bubble cools and it becomes smaller. By repeating this cycle, the bubble oscillates. Well, I actually, well, if you want to see the some numerical calculation related to this bubble oscillation, please read this paper. So far, we know the property of the vapor-rich bubble, and now let's take a look at the flow generation by this bubble. So if we want to control the flow around the bubble, then you may want to know the flow generation mechanism. But actually, the mechanism of the flow generation is not fully understood yet. But now, but we know some factors, and one of these is the Marangoni effect. As I said, that the higher the temperature, the weaker the surface tension. So the Marangoni force is generated like from hot area to cold area. But if we want to generate this type of strong flow, then we need more than 60 Kelvin on this bubble. The temperature difference of over 60 Kelvin on this bubble. It's maybe this is difficult to maintain. So the other mechanism is flow generation mechanism is the bubble oscillation. When the bubble oscillate, they actually induce a flow similar to the Marangoni effect. You can check this paper. Well, now we are trying to measure the temperature distribution around the bubble and see if which is a dominant effect. But maybe maybe we can talk about that next year. But not for now. Well, anyway, the flow is generated from hot area to cold area. So the direction of the flow is expected to be changed by changing the temperature distribution around the bubble. So we try that by adding a sub-laser spot next to the main laser spot. This sub-laser spot can apply temperature gradient on the direction parallel to the substrate surface. And in this case, you can generate the flow in that direction. And similar thing can be done by controlling the spatial distribution of the light absorption like this. So if you have the small patch of the gold thin film, and then if you irradiate laser on this thing on this micro patterned photothermal convergent thin film, then it the heat generation distribution will reflect the optical absorption of this micro pattern. Then by using this pattern, you can control the location of bubble formation and also the direction of the flow, like this. Also, you can use this flow direction control to mix the flow. Like this, it was too quick, but the vapor-rich bubble can steer an area of about 2 millimeters in diameter within a few seconds, even in very thin water chamber. Like in this case, it was 0.1 millimeter thick chamber. And you can see this kind of rapid mixing was achieved using the vapor bubble. So maybe I put too much slides, but so finally I'd like to show you how we can understand this flow using Stokes thread. So because the bubble is really small and the observation area is really large, so you can consider that this bubble as a point force. And you can use the Stokes thread. So the flow distribution around the Stokes thread can be calculated by this equation. And if you apply far field approximation, then this equation becomes much simpler. And by fitting this equation to the experimental result, you can see very good agreement. And so what we can say is that flow generated by vapor-rich bubbles is well represented by the Stokes thread. So let's remind that the Stokes thread, the flow field generated by Stokes thread near the wall is calculated by the Stokes thread and counter Stokes thread. So if you remove this wall, then we should be able to generate a much stronger flow using a single stalk thread without a counterpart. So we nowadays we used optical fiber chip, and we generated the water vapor bubble here, and then generated the flow using this bubble. Now we removed the substrate, and if you if you measure the flow speed created by this bubble, then you can see the bubble generated on the fiber caused much stronger flow over a wider area compared to the bubble on the substrate. And this power is similar to isolated stalk thread. So now we can generate the isolated stalk thread, a point force in the fluid. So here is the summary. What I wanted to say is that now we can generate single stalk thread in the flow, so in the fluid. So we expect to generate arbitral flow by combining several bubbles together. Yes, thank you very much.
Yeah, thank you very much for this nice overview of everything a bubble can create as flow inside a liquid. I'm sure there might be questions.
Yes.
I hope you stay at least a few minutes with us. I mean, I don't know if you talked to Subhasis about staying even longer because it's already late, but anyways. So who has a question?
Maybe I went through too quick. Sorry.
I have one. I raised my hand, but I didn't see your hand.
Hi.
Okay. Okay. Okay, Mish. Yeah. Thank you.
Yeah, thank you for your very nice talk. I enjoyed it very much. I had a question about the oscillation of the bubble. So when we worked on bubbles a few years ago, when bubbles formed around gold nanoparticles, single gold nanoparticles, we also found oscillations in the range of some tens of megahertz, and we attributed that to the Minard oscillations, which are, very simply, the bubble oscillates under the spring constant of the air inside and the effective mass of the liquid outside, right? And this frequency scales a little bit like the inverse of the diameter of the bubble. And it seems to me that, I don't know exactly how big your sizes, your bubbles are, and our bubbles we also could not measure because they were within the diffraction limit, but it seems to me that it scales. I mean, a few megahertz in your case, and some tens of megahertz means a factor 10 about with diameter. So is that the diameter? And then the question, of course, is what is the feedback mechanism that is keeping the oscillation going, right? So can you comment on that? What is your idea? I mean, you mentioned some mechanisms for the oscillation,
yes.
but I'm not sure it's the same. So maybe you can explain a bit better.
Okay. Thank you. So first, our bubble is on the order of 10, like 5 micrometers to 10 micrometers in diameter. And in that case, our bubble oscillates down to sub megahertz up to several megahertz. I think our bubble oscillates in a similar way. We also calculated a natural frequency or any other things, and it was similar to our results. And about the bubble oscillation mechanism, actually, it's still we are working on, but now we think that because the heated area is really small and have steep edge, so if your bubble touch to this area, then it the liquid intensity evaporate and it becomes big. But if it becomes big, then the bubble insulates the heater. Then the liquid or bubble cannot get the heat. Then this fluid part becomes cooler. Then it collapses. Then maybe it touched again, and then the cycle will continue.
Okay, I see. It would be interesting to do theory, right? To
Yes,
make a model
actually,
for that. Yeah.
yes, actually, we followed the model from the All Sensei's group and calculated using like kind of kick oscillator.
Okay.
So it is written in this paper. Maybe you can check it.
Okay, thank you very
Thank
much.
you.
Thank you.
Thank you very much.
Okay, so we would have a little bit of time for another quick question, if somebody wants to ask. Otherwise, I would actually have a question which probably could take longer. I was wondering about the force description you did at the end with the Stokes-Led. Typically, you get a Stokes-Led if you have an external force that is supplied to the system, a body force on the liquid. But now this is an internal force, and the internal force can at maximum generate a force doublet or two Stokes-Leds actually, and then something. So how is this all coming about? I mean, it's
do you mean how I can generate Stokes-Led in using
yes, I
the
mean, yes, I mean, yeah. What was really the origin of the Stokes-Led if you have no external forces but internal forces which are generated by these temperature gradients?
So it's very difficult to understand this flow generation mechanism. But if it is if it is a Malangoni flow, then the shear force on this bubble. Yeah, if you integrate the shear force, I mean the Malangoni force on this bubble, then it can be like a point force.
But because the bubble is pinned, or because if it's not pinned, then it would not be a point force. Or that's due to the pinning.
Pinning.
So the bubble is fixed. I mean.
Yes.
Yeah.
Yes, so I need to fix the bubble to generate the Stokes-Led. Of course,
Okay,
otherwise the
see.
bubble will run away. Yeah.
I see. Okay, so that's why it's coming about. Okay.
Okay, thank you.